Okay, so we want to start talking about application development using the Java Database Connectivity API, or JDBC. When you're programming with a relational database, first I want to start by talking a bit about what our motivation is, what the typical architecture is when working as an application developer against a relational database, really any kind of database. First, motivation. Why do apps even need a database management system? You've known since your first programming class that you can just use files for non-volatile persistent storage. So what does a database add to that? Why would you need it? Well, first, it takes care of a lot of the low-level I/O. When you go program in that first programming class using files, right, you have to do a lot of file management. You have to map out where things are. If it's a binary file, you have to know how many bytes. You have to seek on disk, do these kinds of things. Very low-level I/O. You have to write all the failure code in case your read and writes fail or get locked out for any particular reason. And the database takes care of all that. There won't be any file reading or writing. There won't be any of that kind of stuff. The closest will come is talking about a network connection. Databases provide, usually, most kinds of databases, certainly relational databases, provide transactional integrity, meaning we have a begin and end to our actions or updates or writes to the database, and perhaps our reads as well. Whereas with a file, again, if we get halfway through writing information to a file and it fails, we have to undo what we were doing and redo it again. In other words, we've got to provide that transactional integrity ourselves. And again, we have a nice API for doing this, and the database has a transaction semantics implementer in its query processor, so pretty much we get that for free. Scalability, right? Again, you're programming in a file. If you're used to just writing a desktop application and it's just one file that you're manipulating, maybe you don't think of scalability that much. But think about scalability in terms of having a lot of data that goes beyond what you just have on your laptop. All right, terabytes, petabytes of data in a big data application. Also think about the number of shared applications you may be dealing with. Shared apps in the sense of multiple different applications wanting to talk to the same files, okay? So you're not just writing one program to that file, but many files. How do you deal with that? Again, how do you deal with the concurrent scenarios? As well as multiple users, multiple processes or clients trying to access those files at the same time. Database is going to help us with that. I won't say that it's going to solve that for us, but it's certainly going to help us with that and take care of a significant portion of those problems for us. It provides a clean semantic model. You know from this course that there's an underlying relational data model behind it. Again, when you use flat files, you have to come up with some logical organization about how that file is structured. Again, is it a binary file with fixed record length, variable record length? Is it an image file with a header and metadata? Does it have a footer or trailer on it? So what's the semantics of the data in the side, if you will, the sequence of bytes? If it's textual, is it one line means something? Is a comma separated? What's the delimiter? How do you parse it? All these kinds of things. Whereas with a relational database, we have an underlying formal data model, which you've been talking about in this class and continue to talk about in this class, that will help us out as well. And then finally, we have a uniform standard interface. We have SQL associated with a relational database, which means I already have a very popular language in order to access, as opposed to proprietary in-application code, if you will. So relational databases become so prevalent, they're so popular, they're kind of a de facto solution for managing data from small applications all the way up to large-scale systems and services. Okay, so after motivation, let's talk about application architectures. At a high level, databases use typically one of three of the following architectural styles. These aren't the only styles, but these are kind of the predominant models. The first is an embedded model. In an embedded model, the database runs in the same program, the same process space from an operating system perspective as the application. So that shows a mobile application might be using SQLite. Other embedded databases include Apache's open source Derby project. And the database runs in the same process space. You load a library, it talks to the database. The database typically manages a local file system on whatever environment you're on, mobile, laptop, whatever. Therefore, the app and the database are going to share computing resources like processing speed and memory and the file system. And again, so why would you do that? If you're In an embedded, you typically are just one application talking to the database. You don't have those scalability concerns we talked about. You're not worried about multiple applications and the transactional integrity and the like. Typically, the main benefit here is leveraging that standard interface, making sure you can use the SQL like you're used to using. Often you can even use it as a kind of a developer's test bed before moving something out into the next model, which is client-server. Client-server is kind of the dominant model. The application runs as the client, making network requests to the database server. Therefore, the application and database are now running in distinct processes and typically on different computers. Now, when you do your homework, they may be on the same machine, but they do run in distinct program spaces or process spaces. The calls to the database center are made over the network, so that error represents a network connection. And we're going to talk a lot about that with the API because it's very important to understand the status of our network connection and what it represents. By the way, client-server in a database modality is typically connection-oriented. What that means is when you establish a connection to the database as a client, you keep the socket open until it's explicitly closed, and therefore a lot of your operations that you execute over the socket are stateful. Again, stateful means that the outcome of the previous request can impact the outcome of the next request. And then there's typically many clients. That shows one client, but there's typically many clients for the database at once. There can even be different database schemas loaded in that one database process. That's another part of database server scalability. So you have to be very aware that you have to be a well-behaved client because you're operating with many other users, many other applications also running against that database. Third model, which has been emerging, and I started, by the way, because that's the one we're going to assume for here. That's the one we're going to talk about the most with this API. The third model is database as a service, and this is kind of the newer model of where the database and the data runs as a service directly on the cloud. Excuse me, and applications or other services access that data service via some kind of API calls. So the other app may be a program, it may be a service, could be a web application, again, some other cloud-based service, and the clients use some kind of service interface to leverage those data services. In other words, there's normally some configuration wiring that goes on from an operational perspective to set up, what talks to what and what capacity, what elasticity it shows at any particular point in time. The way we work with databases and connect to them and use them in our code has evolved over time. This slide shows an evolution of, say, the first 2 decades from 70s, 80s up through 90s, maybe 3 decades worth in a nutshell. Since then, of course, the nature of databases has expanded. Big data services on the cloud like we were just talking about, NoSQL databases, things we'll talk about in the last week of the course. But I want to take you up to this point because this is where JDBC came in. Initially, transactions were fed through custom front ends on a mainframe. So you had a mainframe computer with a custom front end and transactions were loaded through that custom front end. They were executed through primarily record-oriented stores, which meant records were like network databases with large tape systems or old school disk systems, if you will, old school storage systems. And things were very batch transaction oriented, a group of operations at a time executing together, if you will. Then third generation languages and routines evolved for the different kinds of databases that were prevalent at the time. Network databases, hierarchical, relational databases. This is mostly 1970s, early 80s kind of stuff, mid 80s kind of stuff. And then from those specific routines that you had to call as a programmer, as SQL became more popular and relational databases became the primary model, embedded SQL became more popular. What embedded SQL did is you would actually write SQL queries directly in your source code. So you're writing a C program and you put directly a SQL query execution. And then a C preprocessor would run, and that C preprocessor would find those queries and translate those to library calls with the appropriate parameters. And that was done for you, that aliasing, that conversion via this language preprocessor. And when it was done, then you could run your compiler and linker as usual. As client server became popular, this was still kind of mainframe era stuff, but as client server became more popular with the PC revolution, it spurred this need to evolve. And what happened was folks came together in the XOpen consortium, as it's called, and developed the call level interface standard. The call level interface standard is an abstract standard with different bindings. So initially you see here it had things like C and COBOL level bindings. ODBC was a binding done by Microsoft in the early 90s, the Open Database Connectivity API. You still, well, I don't think you see ODBC necessarily that unless you dig for it on Windows somewhere. But Windows computers used to ship and do ODBC data sources for everything from an Excel spreadsheet up to a Microsoft Access database, let's say. At the time in the PC revolution, there was a lot of local databases and LAN-oriented databases going on, and ODBC helped with all that. Sun, when it came out with Java, 94, 95 time frame, its first extension API was JDBC, the Java Database Connectivity Model. In JDBC has no relation to ODBC, even though they're named similarly, but they are both derived from the same standard interface, the XOpen interface, because that was a standard at the time. So as I said before, this is just a summary, a very brief summary at a high level of kind of database API and what programmers had to deal with up to about the turn of the century. And from that point forward in 2000s, before we got into NoSQL and cloud-oriented data services, there was really a decade there where the JDBC model and the frameworks built on top of those were the prevalent programming model. We're going to talk about JDBC in this module because it's still the direct data manipulation API. We're going to take some of the concepts and understand the plumbing. Usually when you code against a database, you'll use some kind of framework that may be talking JDBC underneath the hood. JDBC is primarily now a tool vendor API, but it's still useful to understand what abstractions a low-level API is made for the plumbing of how a database works, and that's going to be the nature of our discussion going forward in this module.